Where's that picture? I have a guess.
Where is that picture? Monterey. Okay, so okay, so there's a serious problem with it with Canvas. It's not sending out my emails about assignments. I can't see. I didn't change anything from last quarter when it worked, and some of the students have already checked this, and their settings are set normally. So first thing is homework. The voluntary second validation homework sheet was due earlier this week, and 5 people submitted it, and those need grading.
No problem.
Okay, and you've done it before.
Sorry?
And you did it before last year.
No.
Okay, then in that case, you need my solutions. Come to my office, and I'll give it to you.
Great, thanks.
Okay, but it's very important that you have those. Okay, fine. Okay, so luckily everybody here is getting announcements I post in Teams, right?
Yes.
Okay, if you haven't got Teams notifications switched on, you need to do it. So you get them on your app, on your iPhone, Android phone, whatever, iPad, so that so in the middle of the night you get my messages that I send out to you, whatever. Okay, all right. So okay, right, emergence and order. So this, as I mentioned before, I changed this so that you only have to do one problem, okay, in this homework sheet. Okay, so, well, those do need to be handed in by Friday. If you need an extension, you can have an extension, okay? Just ask for it, okay? I won't give it to you unless you ask, but I've made it really easy, and you only need to do one of the problems. If you want to do all of them, nothing to stop you doing that, because you'll learn a lot. But there's the whole object of the exercise. Okay, then the final of this course. There's no final for this course. There's no midterm for this course. There's a term essay. Okay, just like last quarter, term essay. I've written detailed instructions here, which I'll give to you in a minute. This is when it's due. This is when the final exam of the class would be. This is when it's going to be due, and then sometime around then that week, I will organise that we have a little symposium, and everybody can give a talk about their term essay, just like we did last time. So by May 3rd, send me a title, an abstract, and a list of, say, 5 references for papers that you think are relevant to your topic. Choose whatever you want to do, but that's what you need to do. So let's see what happens if I click this link. Oh, it worked. Okay. Okay, so this is basically instructions. So I want to point out that we're talking in this course. It's about emergence and order, mostly about what the properties of the ordered phase, not about the phase transitions. I mean, you write about phase transitions. I mean, I'm not going to say no, you can't do that. But it really would be good if you focus on the emergent properties of the ordered phase, not on the phase transitions, and you can talk about anything you like. Here I put links to the course at the University of Illinois. So I give some examples here of some topics, but here, let me just show you. So this is the last time I taught it before I came here at the University of Illinois. The first thing you'll notice is, look how many people took this course. The credit, okay? Not including all the people who took it for observing, okay? This was probably the most popular graduate course there in condensed matter. So, and most of these people were experimentalists. So I don't get it. Cosmic strings, odd viscosity, flocking, blast transition, emergent ecology, evolutionary game theory, Turing pattern formation, networks and complex systems, coarse graining of metabolic networks, topological solitons and liquid crystals, electron pairing and ion-based superconductors, macroeconomics, superfluidity and superconductivity in neutron stars, the conformal bootstrap, topological defects, active flocks, entanglement, criticality, measurement-induced phase transitions, criticality in living matter, Anderson localization, and inflation of the universe. Okay, that's what the students at U of I did in this. So lots of different things here. Okay, so that's that. Okay, I don't think I wanted to tell you anything more about that. Now, the next thing I want to talk about is okay, so the front page of the course is this one, which you've seen, and I want to draw your attention to this. So this is the emergent states of matter, emergence in order movie page, where you can ignore this one because this was some video that was from some course I gave somewhere else. And what is all that thing about climate change? Huh? Okay, this is important. We're about to get on to looking at quantum order, and so we're not going to go into the deep dive in superfluid helium that we did last year. I'm going to do it, and we're going to do it much more superficially because I want to get on to other things. But I do want you to know about it. So this is a video. This is a historic and famous video. It was made by a person who discovered superfluidity, who should have got the Nobel Prize, but didn't. Kapitsa got the Nobel Prize for it, even though he wrote his paper first. You can read all about that here. This movie took 10 years to make, and because you're literally viewing macroscopic quantum phenomena in a cryostat, and so this movie was literally a movie, and then I got this movie. I got the actual movie, the big roll of film from John Bardeen, who's my colleague at University of Illinois. John, do you guys know who John Bardeen is?
BCS.
How many Nobel Prizes did he get?
2.
Okay. In which subject?
Physics, matter, transistor, and super.
Okay, so you know too much. Yeah, he got 2 Nobel Prizes in physics. He's the only person to do that. There's another person who's got 2 Nobel Prizes in the same topic. That's Barry Sharpless. He's here at the Scripps Research Institute, and he's a friend of mine. He got the Nobel Prize twice in chemistry. Okay, and I only know him because he got interested in evolution. He wrote to me saying he wanted to talk to me about evolution. Like a few months after I came here, and I said, well, sure, I'll just walk to your office. And I moved here. He thought I was still at the University of Illinois. So I've at both my universities I've been at, I've had a colleague who has won 2 Nobel Prizes at the same time. So Jack Allen got 0 Nobel Prizes. Anyway, I took John Bardeen's film, then I digitized it, then I scanned it, then I uploaded it to. I digitized and scanned it, and then turned it into a video. Well, originally I turned it into a DVD. I ripped the DVD. Then I uploaded that to YouTube, and got permission from them to do it. So you should watch this video because it is amazing. We're going to be about to talk today about quantum vortex lines. So I want you to know what quantum vortex lines are. So here's a YouTube video that we made in my group many years ago on quantum vortex line dynamics using a very fast numerical method that we invented, which is based on the normalization group, which can then simulate huge quantum systems and things like this. Actually, this work was never published. But anyway, anyway, so you can see these movies up here, and we're going to talk about superfluidity. We're coming up to talking about superfluidity, and we're going to start talking about it today when we talk about constant hours. Yeah.
The vortex lines that you just showed. So my understanding is these vortex lines are the fundamental defects of the.
Yeah.
And are they now ordering? Is that what's they're forming now their own structure? So this is a structure out of defects? Is that what I'm seeing, or is
No.
that just?
No, in this thing, the flow, the superfluid is being perturbed externally by a propeller, and then these quantum vortex lines are
Being generated.
uh,
Excited.
how do I? Oh, go away. How do I? Why do I have this stuff? I don't want Fox News on my screen here. God, terrible. Okay.
Press
Are you trying to
bottom.
replay it?
No, I can just reload the page. I don't want to anyway. But anyway, I do suggest that you look at that web page,
No problem.
and
If it's being generated, then that geometry must have come from the generation technique, whatever.
yeah,
it
so
was.
the geometry was
Yeah.
generated by external forces.
Okay, okay.
And quantum vortex lines, if you have a bucket of vortex of fluid and you rotate it, the quantum vortex lines will order into a regular lattice, as you know.
That's what, but I thought that was a whole new structure that I saw, and it didn't show the geometry.
It was, and there's other videos there which show different forcing. One of the things that we discovered in about 1993 or so is that if you take a superfluid and make it turbulent, the quantum vortex lines will follow the high iso contours of vorticity in the normal fluid, and so superfluid helium, when it's made turbulent, actually behaves like a classical fluid, even though it is quantum. And then you can observe the quantum mechanics. You can observe the decay of turbulence using tools from quantum mechanics. Okay, so let's get back to our class. So there's a whole bunch of announcements. Any other announcements? Any other questions before I go on to doing science? Okay, so let's. Today we're going to continue where we were last time, and last time we had introduced the idea of we introduced the idea of Goldstone modes, and we discussed what those things look like. I just want to find my page here. Okay. Yeah, so last time we talked about Goldstone modes. We talked about what they are physically. We talked about how to compute their consequences. We talked about general elasticity theory, which I'm going to say a little bit more about. So we talked about, for example, the emergent elasticity theory for things turning into solids, where you get the elasticity theory that we're all very familiar with, and that is just a generalization of what we did for looking at systems with continuous symmetries. So this was the rigidity, the stiffness, which is related to the gradient of the phase of the order parameter as it is being excited, as the transverse modes are being excited. So what I want to do now is, at the end of the last lecture, we very quickly talked about the lower critical dimension. So we talked about the stability of the ordered state. We looked at the most dangerous fluctuations. And I did this very quickly for you, showed you that if I look at the transverse correlations, those seem to diverge as we go towards 2 dimensions due to a logarithmic divergence at the lower limit. And that logarithmic divergence prevents the occurrence of 2D order. So what I want to do today is I want to continue that. I'm going to just do that for you in a slightly different way. Then I'm going to show you how the first topological phase transition was discovered. We're going to talk about the Kosterlitz-Thales transition, and that will lead us into a discussion of quantum vortices. We will see that quantum vortices exist in these in these sorts of systems with continuous symmetries, and that they actually are responsible for a very strange type of phase transition. And that will then lead us next week. We will be talking about quantum order and topological defects in more detail. Okay, so let's start, and I want to start by uh, by by talking about the Merman-Wagner theorem. So this is section 4.12 in my ESM notes, not in my renormalization group book notes. Okay, so you have those notes as well. They're on the canvas, so that's what I'm going to be following here. So this is no no-go theorem, no long-range order in D equals 2 if you have a continuous symmetry. So what I'm going to think about is a system where n is equal to 2 and d is equal to 2. So it's an XY model in 2 dimensions. So you can think of this as being, say, a superfluid in 2 dimensions. And it's a superfluid because the superfluid has a complex order parameter, so it has 2 components, the real and imaginary part. So it has 2 components. So I want us to think about the following. So here is the top-down view. So this is x1, x2. Actually, let me just change that. I'm not going to say that. I'm going to say it like this. S1 and S2, and then the order parameter is a vector like so, and so I'm going to call this direction. I'm going to call this direction like the x direction. I'm going to call this direction like the y direction. Just because it's quicker to write. So then this angle here is if I call this angle phi, then the projection of S onto the S1 axis, the x-axis is just cosine phi. And remember, S itself has magnitude 1. So what that means is that if I look at the order parameter, which I will call psi, so it's a vector. So it's going to be Sx, psi x, psi y. I can write down that the expectation value of psi x is going to be the expectation value of cosine of that angle, cosine phi. And then what is that? So that is the real part of e to the I phi. That's what a cosine is. And then it's an expectation value. So this expectation value I can write in the following way as the functional integral over phi. So I'll write that as d phi, and then I have e to the minus beta times the Landau free energy over z. That's my probability distribution, and then my e to the I phi. So that tells me if I wanted to compute cosine phi, I would do this integral of the Landau free energy and then of e to the I phi, like so. And this object is going to be a number that I'm going to define to be e to the minus w. Now then, what do I mean by L? So L is a Landau free energy, and what happens is if I'm at low temperature, so temperatures lower than Tc, then the amplitude fluctuations are frozen out. And what do I mean by frozen out? Well, let's go back to last lecture. I had a picture of the Landau free energy. So there's the Landau free energy, and what we've seen now several times is that the transverse fluctuations go around the minimum here, so they are gapless. The fluctuations in the longitudinal direction cost energy. So if I lower the temperature, the thermal energy that is available to excite the longitudinal fluctuations will be too small to make them do anything. So basically, if it will essentially be stuck right in this minimum here, it won't be fluctuating in this direction up here if I'm at low temperatures. So that means that at low temperatures, the only degree of freedom that is left is the transverse degree of freedom. In homework one of the exercises is to do that and to do this calculation. Okay, that's one of the exercises. See, write down the order parameter in terms of amplitude and phase, and then freeze out the amplitude fluctuations, and you get the effective theory in terms of the transverse. Okay, so but we basically did that last time. So they're frozen out. So what that means is that there's not enough thermal energy to excite the longitudinal modes. I've called them amplitude modes, longitudinal fluctuations. The amplitude and longitude are the same thing. We've got a complex number, so the amplitude is the longitudinal direction, the phase is the transverse direction. Okay, so there's not enough energy left, and so what that means is that I only get the transverse modes, transverse or phase modes are the only ones that can get excited. And we went through that last lecture, so I'm really just reminding you what we did here, where we wrote down the free energy of the system as, where did I write it down? I know I wrote it down. Where did it go? I don't get it. Well, did my notes not synchronize? Yeah, here, this part. So we worked out the effective free energy in terms of phase variables. There was a longitudinal contribution, and this was the transverse. For a minute, I thought I was really losing it. So, which I might be, doesn't prove that I'm not. So that means that I can write down the Landgraf free energy as 1/2 times some coefficient, which I'm going to call rho s, times the integral of grad phi squared, and then it's d dr, but d is going to be equal to 2. Okay, now here's the thing. You might say, well, I've got to do this functional integral. What do I do here? Think about this. When I do it, if this was a one-dimensional integral dx e to the I, e to the something, times e to the I x. This is a Fourier transform. So you can ask yourself, if I write down what is the expectation value of e to the I phi, where this expectation value means that the probability distribution of phi is some Gaussian. So it goes like e to the minus phi squared over 2 sigma squared over 2 pi sigma squared square rooted. If I'm lucky, then that is normalized. I think it is. So if I have that, then I do the expectation value of e to the I phi. That expectation value of e to the I phi is then easy to compute, and it is just e to the minus 1/2 the expectation value of phi squared. So if I have a Gaussian distributed variable, so this theorem is true for any Gaussian random variable. Very useful thing to have in your back pocket. So what that means is that if I want to compute this expectation value of psi x, which is this thing called e to the minus w, then we can just read off that w then is just the expectation value of phi squared times 1/2. And the expectation value of phi squared, well, that's the magnitude of phi. This is phi, this is the correlation function of phi at r, the correlation function of phi of r and phi of r prime. Well, r prime is equal to r, so that's phi of r squared. So this is phi of r squared, and so that is equal to the transverse correlation function at k equals 0. Actually, that's not true. It's equal to the transverse correlation function at r equals 0. So what is the transverse correlation function? So that is the integral d dk, and then e to the I k dot r minus r prime, evaluated at r equals r prime. And then I'm going to do this integral d dk over 2 pi to the d, and then the transverse correlation function goes like k squared, like that. And there's a factor of rho in here somewhere. Probably down here. Okay, so that's the thing that I basically wrote down last time. So if I said r equal to r prime, then this thing is just 1. So what you can see then is as for d is less than or equal to 2, there is a logarithmic, well, if d equals 2, there's a log divergence at k equals 0. And that's what I showed you last time. And so what that means is, therefore, w is going to infinity. And so if w is going to infinity, then that means that the expectation value of the x component of the order parameter is e to the minus w is going to 0 as for d equals 2. And so what that means then is that the average value of the projection of this spin on the x-axis is 0. I look at if I do the projection onto the y-axis, I would get the same result. So what that then tells me is that in d equals 2, the expectation value of my spin vector is equal to 0. There is no long range order. In the classical sense. Okay, so that's a better way, a more precise way of doing what I showed you last time. Any questions about that? Yes.
Can you elaborate on why phi is normally distributed in this case? So
Sure.
I mean, I believe this expectation for a Gaussian random variable, but L.
I'll show you why.
Okay.
I'll show you why. Because here's our probability distribution, or here is the thing that is in the probability distribution. So if I took the Fourier transform of this, this is 1/2 rho s times the sum over k squared times phi k squared. Right? So the probability distribution for every Fourier component is just Gaussian and phi k.
But then wouldn't that mean that, so you're saying that the Fourier components are normally distributed. So then wouldn't that theorem only apply to e to the I phi k?
Well, there's nothing, when I write down these path integrals, we're doing everything in k-space.
Okay.
Right, so this function integral over phi is the product over k d phi k.
But like when you write e to the I phi, then do you have to substitute phi equals sum on k, phi sub k?
Yep. So every term in this integral here, is linear in phi k. All the phi k modes separate out.
I see.
So you can do it mode k by k and then reassemble it.
I see.
And you can do it in real space too, by the way. I mean, you can I haven't written it down for you in terms of functional differentiation and so on, but you can do all of this in real space too. But it's just trivial in K space, because then everything is just factored out mode by mode. Okay, so if you want to check this, first of all, do this with phi being a scalar, being one variable. Then do it with phi being a vector. Phi is a vector, then the analog of this, thing, if phi were a vector, would be, so let me just add this as a comment. So the comment is, if you try this with phi equals a scalar. Okay, so literally just what I wrote down on the previous page. Then try it with phi being a vector. So then the probability distribution for the vector phi would be proportional to e to the minus a ij phi j, and it would be over the square root of the determinant of a, or something like that. Okay, so go ahead and do this, and then you can do this with phi k components. Okay, so then you can check this result. Okay, any other questions? Okay, so now I want to talk about the Kosterlitz-Thouless transition. I'm going to use the Kosterlitz-Thouless transition to introduce our first topological excitations of the system. And so this is in my normalization group book, section 11.2. So what I'm going to do now is more or less recapitulate what's in the homework. Okay, so but I encourage you to work it out yourself. So the goal here is to look at n equals 2, d equals 2, and see a topological phase transition. Even though there is no local order parameter. So it's called a topological phase transition because we're going to have a transition into a topological phase. And as a topological phase, topological means I have to take a path in some plane. I have to look at some global quantity in order to detect the order. So if I just sit at one point and just look at the magnetization like I do in a magnet, I can see that the magnet is ordered just by looking at one point and just seeing all the spins pointing up. I can't do that in a topological phase. So when we talk about topological phase, what I mean is that a topological phase is global, not local. And I need a topological invariant to detect its existence. So here is what we did in the homework. So, or at least I did. I don't know if you've done it. You start off with our order parameter psi of r, and I'm going to call this as S1 of r plus I S2 of r, just like I did before. And I'm going to write the Hamiltonian in the following way. There's going to be some constant, which is the zero of energy. And then I'm going to write it like this: integral d dr grad psi squared absolute value plus u naught over 4 times something clever. We're going to write this thing as psi squared minus the absolute value of r naught over u naught squared. So this is my free energy. So you say, well, wait, why does it look like this? U naught over 4, and then the whole thing squared. But this perfect square has got a psi squared inside it. So if I expand this out, it's going to be something like psi squared, and then psi to the 4th, and then some constant. So this is just as good a way of writing down Landau theory as the normal way that I've done it. Okay, but the reason that this is really useful is that we can is that what we're going to do is we're going to see that the low temperature, the amplitude fluctuations are suppressed. So let's think about what that means. So this term psi squared, that is the amplitude squared. That's what I mean, the amplitude squared of the order parameter. So the amplitude, so psi, its magnitude is not exactly equal to 1. Okay, it's mostly equal to 1. In fact, it's mostly equal to this thing. Okay, so in other words, this is a soft spin representation of an XY spin model. So let me just say what I mean by that. When I say the words soft spin, what I mean is that the magnitude of the spin, or the magnitude of psi, is not necessarily equal to 1, okay? Or equal to some constant, it can fluctuate, okay? So before we talked about, say, an Ising model, an XY model, so I have spins with magnitude 1, and all they can do is point in different directions. What we learned last quarter was that, and what we talked about this quarter, is I can make a Landau theory of such a system. And in the Landau theory of the system, the spins do not actually have to have the same magnitude. Their magnitude can fluctuate, but the behavior of the system is still mostly the same as what I would have if the behavior was exactly constrained to be exactly a constant size. So when I say an XY spin model, what I have to say is that the magnitude of psi at every point in space is exactly equal to 1 with no exceptions. So that's a constraint. Constraints are hard to deal with. Constraints are bad because they impose an extra equation. So you've got to do statistical mechanics with this constraint applied to every point in space, which you can do, but it's silly to do it. Okay. So when we talk about a soft spin model, the soft spin means that the expectation value of S is mostly around a fixed value. But it can fluctuate. So let's have a look at what we have over here. So you can see that this is a number times this thing over here. Okay? Forget about the gradient term for now. Okay? So imagine that this was a number, let me call it gamma or something like that. Let's suppose I make this number go to infinity. Okay? That would say that this energy is going to be infinity unless psi squared is exactly equal to this number. Okay? So that would be a way to make this a constraint. Okay? So if I set this number equal to infinity, then this thing would be exactly equal to this. Any other value of psi, this Hamiltonian would have infinite energy, and then e to the minus beta times the energy, which is the probability distribution, the Boltzmann distribution, would be 0. So So when we have e to the minus, say, some lambda times psi squared minus r naught over u naught squared, if lambda equals infinity, that means that psi is forced to be the square root of the absolute value of r naught over u naught, okay? But if lambda is less than infinity, then psi is mostly around this value. The probability distribution is not a delta function; it's something else. And the lambda equals infinity value is then just a delta function. So we don't care whether it's a delta function or something focused around that. And so we call that lambda less than infinity, where p of psi is some e to the minus lambda psi squared minus r naught over u naught squared. This is a soft spin model. So that's what it looks like. And if I were to plot the probability distribution in the so this is psi. This is the probability distribution of psi. So in the hard spin model, it would look like this. And in the soft spin model, it will look something like this. Okay, so that's the picture. Is everybody happy about this description? So then, what we can say then is that when u naught is getting large, we can say that psi of r is basically going to be the magnitude r naught over u naught times a phase e of r e to the I phi like that, or e to the I use the notation theta, and so therefore then the effective Hamiltonian in terms of the phase angle theta is just some number k over 2 times the integral d2r of grad theta squared. So theta is what I call it phi over here. It's phi if you turn on the side like this. You can see that's a phi. If you have it rotated like that, it looks like theta. So it's the universal symbol. Okay, so that's what the Hamiltonian looks like, and the value of this coupling constant is then r naught over u naught. Okay, now the thing about this is that theta or phi is a phase angle, and so is periodic. So the configuration where I've got psi of r, in the configuration where I've got theta of r plus 2 pi times n, where n is an integer. That's not the symbol for an integer. Let's try again. When n is an integer, this configuration and this configuration, these are the same. So when we do this functional integral, we're mostly going to be neglecting this, but actually we're going to need to worry about the periodicity of the phase. So we have to worry now about the winding of the phase as I go around in the angle plane, and that's where the topology is going to come in. Okay, so there's so we can compute phase correlations. And the way we compute the phase correlations, first of all, we're going to ignore the multi-valuedness. So we're going to ignore that. So if we assume this assumption is true, this is reasonable. A small grad theta, and so then we can then take the limits of the integral to infinity. And so if I want to compute the 2-point correlation function, so the 2-point correlation function of the phase is then the expectation value of theta of r minus theta of r prime. So this is the order parameter correlation function. The magnitude or the amplitude of the order parameter is fixed, and so the order parameter correlation function only involves the phase. Because the amplitude is fixed. There's no amplitude fluctuations. And so since the order parameter is psi of r prime, so this thing, all this is just, I can see people are looking confused, so maybe I went too quick. So this is just psi of r prime. That's what the 2-point correlation function is. Well, psi is amplitude times e to the I phi, so all I need to worry about is this. Okay, so then we can use our theorem for Gaussian random variables. So I know that this g of r is then equal to e to the minus 1/2 the expectation value of theta of r minus theta of 0 squared.
Is one of the sides complex conjugated?
Yes, because yes, it is. Thank you very much for pointing this out. And by the way, this r prime is really is 0 because I've just written this as g of r. So yes. So when I'm looking at this, I'm looking at the psi with its complex conjugate. So this is the absolute. So this would be. This would correspond to looking at off-diagonal long-range order. I was looking at if this was a quantum system. We'll say a little bit about that later. But yes, here I'm defining it to be the complex conjugate. Thank you. Thanks for reminding me. Okay, so now I have to compute this. So now let's write down what theta of r looks like. So we know what the correlation function is for the phase, because we know that the Hamiltonian for the phase is just k squared phi squared. So we know that the correlation function is then just 1 over k squared. Just reading it off by fluctuation dissipation theorem. So then we can read off that expectation value of theta r minus theta 0 squared is then 1 over k, and then the integral from 0 to k dk over 2 pi times, let me write it in a slightly different way. Let me not skip a step. So this is d dk over 2 pi to the d, and then it's 1 minus e to the I k dot r over k squared. So that's what the integral looks like, and then d is going to be equal to 2. So I'm going to replace that with a 2 and that with a 2. So that's what this correlation function actually looks like. And now we have to evaluate that. And why? How do I know it looks like this? Well, because I can read off that the expectation value of theta k squared is just the 2 over k times k squared. And I know that from over here. Okay, so if you work that out, this thing here is the integral representation of a Bessel function. So you can work this whole thing out, and so I'm not going to go through it, and it's not really that important. So 2 over I'm going to write this like this: 2 kbt over oh, I had it right before. It's this times integral from 0 to lambda dk over 2 pi 1 minus the spherical Bessel function over k, and this ends up being k this ends at 1 over k times pi times the logarithm of r over lambda to the minus 1, where r is much greater than lambda to the minus 1. So this logarithmic dependence of the correlation function is this logarithmic divergence that we saw earlier for 2D. So, but here's a thing that's interesting. Okay, so this is this thing over here, but this thing comes into this correlation function over here. So what that means is when I compute what the correlation function looks like, so g of r, which is e to the minus 1/2 times the expectation value of theta of r minus theta of 0 squared, I've got an exponential of a logarithm. So what is e to the log x? E to the log x is just x. So this thing is then r. You learned it on your mother's knee, right? So g of r is just r to the minus eta, where eta is equal to kbt. Well, never mind kbt. In the units I've used over here, 1 over k times 2 pi.
I could have said.
And hang on, wait. Okay, no, let's forget that. So this k that I have here, which I wrote down over here, this k is basically j over kbt, where this j is like the nearest neighbor spin interaction. So there is a kt floating around, because when I write down statistical mechanics, I have to absorb I've absorbed the factors of kt into this. So why do I mention that? Because what that means is that g of r is like r to the minus eta, and in physical units, eta is kbt over 2 pi j. Okay, now this is really weird, Why is this weird? Because as we saw before, below TC, remember we're way below TC. We're not looking at a phase transition. I have power law correlations, even though I'm not at a critical point. Those power law correlations are due to the phase degrees of freedom. So they come from the Goldstone modes, but the exponent is not a half or 3 or something like that. It's a number that depends continuously on temperature. So the exponent continuously depends on temperature. And we are well below TC. So that's very, very, very strange. Okay, so now let's see what this has to do with the Kosterlitz-Thouless transition. So what I've shown you is that since the phase if I start over here and look at how the phase varies of the order parameter as I go further and further away, that thing scales like the logarithm of R. And so there's no long range order. The further away I go, the more disordered the system becomes. Okay, so this is another way of seeing that there is no long range order in D equals 2 for the system. Okay, now let's do something. Let's think about this in another way. Okay, so this calculation is a spin wave calculation. All I did was assume that the fluctuations are small as I go along in space. And so I neglected all the problems due to the phase actually rotating by multiples of 2 pi. I ignored all that multivalueness. Okay, so this is so this is first of all, this is a spin wave calculation. Second of all, this calculation says that the order parameter correlation function, order parameter correlations, do eventually decay to 0, but they decay with a power law, with a temperature dependent power law. Which is also temperature dependent. So there's lots of things that are weird here. First of all, the order parameter correlations decay to 0, but they decay with a power law, not with an explanation. So let's draw what the correlations look like. So here is space, there is R, and what I'm going to compute here is the 2-point correlation function. Like this, I'll put psi 0 if you want. Okay, so what would we expect to happen if we had long range order? If we're above TC, let's normalize this to be 1 at the origin. What we expect to happen would be that as I'm above TC, we already saw this, that the correlations decay exponentially. We computed that before. So above TC, the correlations will decay as e to the minus r over the correlation length, and this would be true for t greater than tc, for any physical system that is ordering. If the physical system is ordering but below tc, then this thing is actually going to go exponentially to a non-zero value. So this one here is also exponential decay, but it's decaying with a critical, with a correlation length, which is psi less than. So this is true for t less than tc. And then this value here that it decays to, that is psi squared. Right? The system orders to psi squared. So in other words, the correlation function. So this means at long distances, the correlation function decays. These psi of r and psi star, psi of 0 become independent. So this thing factorizes and just becomes this. So this is what we've seen before. This is magnetization. So this is called long range order. Because as r goes to infinity, psi of r, psi of 0 goes to the average value of psi squared. So that's long range order. It's order because it's because of psi squared, and it's long range because the correlation function asymptotes out to a non-zero value as r goes to infinity. So the r goes to infinity is the long range part of long range order. So the long range part is that, and the order part is this. So this is what normally happens. This is what we've been doing this quarter and last quarter when we were looking at the actual phase transition. That's what we mean by long range order. Now, what we've discovered in the costless-Thours transition is something completely bizarre. What we've discovered is that we can have an order which goes like that. Of course, I've drawn it really terribly. So this is for t less than some tc. So we don't know what that tc is, but it goes like r to minus eta, and it asymptotes to 0. So that's what happens in n equals 2, d equals 2. So we've got power law to something 0. Now, that can only happen if there's order. That can only happen if I have this phase order, but at very high temperatures, my 2D system must be a paramagnet, so it must have this behavior. So there's a paradox here. And the paradox is this. So we've seen that there's a very so I'm going to walk this back here. I've said this is t less than Tc, but what I really mean is that this temperature is going towards 0, a very low temperature. So what that means, so what I want to say then is that for t going to 0, I have algebraic decay to 0, of the 2-point correlation function. Well, we know that at high temperatures, temperature going to infinity, what we must have is strong fluctuations both amplitude and phase. And then that should give us exponential decay to 0. So the paradox arises because I'm contrasting slow algebraic decay to fast exponential decay. Because the decay is in this phase algebraic, that's why it's very slow. So if I have a system with a finite size, by the time I've got to the end of the system, it's never decayed because it's only decaying algebraically. Whereas if I have exponential decay, it decays very rapidly. And as long as the system is bigger than the correlation length, it'll go to 0. So that's another way to say I can kind of get 2D superfluids, 2D superconductors, 2D long-range order in a finite system, but only because the algebraic decay is so slow. So at low temperatures, it's algebraic. At high temperatures, it's exponential. So that means there must be a point in the between where it crosses over. There's no alternative. There has to be something in between where it's algebraic at low temperatures and is exponential. Is exponential at high temperatures. So I'm going to get this picture. So here is temperature. So what I know is here's 0 temperature. Here there's algebraic decay of correlations with distance. Up here there's exponential decay. So somewhere in the middle has to be some kind of transition. It has to be that. Something happens. And so that's the Kosterlitz-Towers transition. So we're going to call, so this thing is true. So yes, and this thing is the Kosterlitz-Towers transition. Okay, so let's now talk about it.
Quick question.
Yep.
On this correlation function plot that you have here, so you're saying at height above the critical temperature, it is a paramagnet. The correlation goes to 0 and psi squared goes to 0.
Exponentially.
Exponentially. Then below the transition temperature, you're saying it still decays exponentially, but there's some ordering.
Yep, that's the normal picture. In fact, in the homework 1, I asked you to calculate everything that I did in class below TC, remember?
Right.
And below TC, the only difference is that now there's a non-zero expectation value of psi. When psi expectation value is 0, just go like this. When psi expectation value is non-zero, it goes like this.
But you're saying that if I then cool it even further to 0 temperature, that long-range order goes away?
No.
But that's what this plot seems to imply, unless I'm
Do you
misunderstanding.
mean this thing here?
Yeah,
This is only true for n equals 2, d equals 2.
I
These things
see.
are true generally. Okay, so this thing over here,
I see.
so this thing over here is the usual case, canonical case. So that's that and that. That's the standard picture.
I see.
N equals 2, d equals 2 is weird.
I see.
It was the first example of a topological phase.
And then is there any reason why, like in the Ising model, we say the correlation function is that term minus psi squared? Is there a reason why we don't subtract off psi squared in this case?
No, we do subtract it off, Here I'm just defining G to be this
Right.
operator. Okay, which is true above TC. Below TC, it goes to this. So when we say define for me a correlation function, I'll say, okay, it's the correlation function of what? It's the correlation function of the fluctuations. The fluctuations of psi minus the average value of psi.
Oh,
So-
but average value is 0.
Yes.
I see. Okay, thank you.
Okay. So what's going on? What's going on? So this is section 11.2.3 in my book. This is vortex unbinding. So let's make a picture. Okay. Okay, so there's a picture. This is a picture of a configuration of a vortex with unit topological charge. So this is an order parameter. It has an amplitude which is given by the length of those arrows. I start over here and follow the arrow round. It goes round like this, goes round like that, goes round like that. And by the time I get back to the top, it's rotated by 2 pi. So we say it has topological charge of 1. Suppose I had an order parameter and a topological charge of 2. So it would do something like this. We go round, we get back to here at the bottom, then it would go round and get back to here at the top. I did it too many times. Let me try again. Okay, so it goes round and then back to here, and then goes round and then back to here. Okay, that's that. There I did it correctly. So it can go. I can go around that loop, and it will rotate twice. So the topological charge is this. In this case, it's n equals 1, and what I did for you was a charge of n equals 2. So what is the topological charge? So let's imagine that I take the line integral around any curve of grad theta around here. So I'm going to imagine that I choose any curve I want. So there's a curve C. I go around that curve. And that curve can be like here on the page, or it can be 100 miles away. Okay, and I draw this configuration going out 100 miles, and I trek out 100 miles and walk around that curve. And when I get to the end, I would have gone round once. Doesn't depend on the distance. So this number is 2 pi times n, and it doesn't depend on the radius of the curve. Why is this happening? Well, if we look at what grad theta dot dr is, so that I can write it down. It's d theta by dx dx. Well, let me write it down in this way just to really show you that I'm not cheating. So it's this vector d theta by dx d theta by dy, dotted with the vector dx dy. Okay, that's the vector dr, that's the vector grad theta. And if I look at that, so that is d theta by dx plus d theta by dy dy. And so that is just d theta. Okay, theta is a variable that depends on x and y. So by just the calculus that you learned on your mother's knee, that's just d theta by dx. So what that says is that when I integrate round this curve of dr dot grad theta, that is just the change in theta, and that is a number that is 2 pi n. And so that's how we know that. That's how we know this. And it has to go round an integer number of 2 pi's because the order parameter itself must be single valued. So the order parameter psi equals some amplitude times e to the I theta. So this must be single valued. But the phase can be multi-valued. And so this is this configuration is called a vortex. Okay, so I have 2 minutes left. Let me not rush it. So I'll spend the first 5 because we started late because all the things with the figuring out the course announcements and things like this. So next time we will finish this. We will I will work out for you the energy of one of these things. Then we will work out what the entropy of those things is. And then we'll see that there is a phase transition, again using a very similar argument to the one we used at the beginning of the course when we saw that phase transitions didn't happen in one dimension. So we'll do an energy versus entropy, and we'll see that there is a transition, and we'll compute the transition temperature of this transition here from this configuration. Okay, any questions about today's lecture?
So we are only calculating the phase transition in d equals 2 and n equals 2.
Everything is d equals 2, n equals 2.
Yeah, like in other dimensions, will this transition exist?
No.
Oh, I see.
Okay, this only happens in 2 dimensions for n equals 2. So I can give you a homework sheet where you can start looking at what do topological defects look like in other dimensions. Okay, so if I were in not 2 dimensions but 3 dimensions, what do you think this thing would look like? A line. Why? Because you know the answer.
I know that already.
Well, why? Well, how do you know that mathematically? Okay.
Discontinuity of the phase. I don't know. Yeah.
Okay. So here's a way to think about it. Okay. So actually, let's do this. Let's have this. This is an important discussion to have. So let's answer this question. But let's do it next. Let's do it next. Okay. So but anyway, you're clear that this is everything I'm doing here is exactly n equals 2, d equals 2. Okay. N equals 3. This doesn't work either. Okay. Okay. And n equals 2, d equals 3. This also doesn't work. Okay. Any other questions? Okay. Is everybody on track to hand in homework 1 by Friday? To do 1 question. If you need an extension, just email me, and I will then reply to you saying you have an extension granted. Okay, there's lots of good reasons for that. For example, the homework, the homework, you didn't realize the homework had been sent out because of, so yeah, I know you've got other things to do. So just email me, and I will reply and let the grader know, and Mustafa will have my solutions and can grade them. Okay. Any other questions? Okay, I will post the lecture notes and the videos on Teams, which amazingly is more. There's products that work even less well than Microsoft products. Who knew? Okay.